Started the recording. Yeah. So unit 4 has energy methods. All right. And we have within the energy methods, work energy principle, Castigliano's theorem, unit load method. Of these Castigliano's theorems is the most important, and next is unit load method. Okay, unit load method is the principle of virtual work. We'll explain the concept. Now we need to do evaluation of deflections for statically determinate beams and trusses. Okay, and Maxwell's theorem and Betty's law, it is just we will not apply in problems, but just you should know their application is in trusses and plane frames, but we should just know that. Next important is redundant trusses and frames, of which you know even if you do trusses, that is sufficient. Mostly you get um, trusses problems only, not so much when frames problems. So now, although this is small, you see a lot of coverage is required for this. So first of all, let us see the notes that I given you. All of these notes. This is the notes that I've already uploaded, and soon I'll give you other notes also. For today's problems, whatever I'm discussing, I'll be sharing with you. So basically work done by a force is F integral F dx from 0 to delta, whatever it is. And generally, in simple words, work done by a force is force times the displacement in the direction of force. So this is work done by a force. Now, when the force is gradually applied, that means when we are applying the load P, it is not that there is a sudden application of the load. It gradually increases from 0 to P. Then, in that case, work done will be half times P into delta. This is the area, the integral area. F will be P by delta times X. So when we integrate, you will get half P delta. You just have to remember this when for gradually applied load. So like here, there's a bar and we apply a load gradually. So it produces a deflection delta. So the work done by this force P in moving, in causing this deformation delta is half P delta. So this is gradually applied. But if there's a suddenly applied load, it may not be suddenly applied. Let's say first P is applied. Okay. Then after that P dash is applied. So P is already existing and then P dash is applied. Then P dash will produce an additional deflection of delta dash. Okay. So work done by P dash gradually applied will be half P dash delta dash, because this P dash has only caused this much additional deformation delta dash. However, P is already existing. P is already existing and P has moved through a distance delta dash. So work done here, it will not be a gradually applied load. It is already a fully existing load. So the work done in this case will be P times delta dash. Okay. So this you have to remember. So work done by both the forces for getting this is this. This is conceptual remembrance only. So you don't have to go deep into this. Okay. Work done by moment for rotation is half m theta. Same concept here. Now, strain energy is the energy stored in the body due to deformation of the body. by the external forces acting on it. This concept is very, very important. We will be using in Castigliano's theorems. And then strain energy concept is very important, and work done by externally applied force. So strain energy stored will be equal to the work done by externally applied force. So very, very important. This equation is very, very important for trusses. Note down in your notes, in the notebook that you are having right now in front of you, this slide number 9 of this notes, energy methods, the basic notes which I had covered earlier. So slide number 9, this, the strain energy stored for a due to axial load in a bar that is deforming axially, axial deformation. So this will be used in trusses. Trusses is a axial force members. Uh, so half P delta will be the strain energy stored equal to work done. So work done is half P delta. Now by Hooke's law, this delta deformation is PL by AE. Stress upon Young's modulus gives strain. So stress is P by A upon Young's modulus. So P by AE gives strain. Strain multiplied by length will give deformation. So delta is PL by AE. So this U is P square L by 2AE. This is the strain energy stored in the bar. Very important for axially loaded bar. Okay. Next, of course, this you can study. I'll not go through. I have to cover big problems. This you can go through for short answer questions. What is the definition of modulus of resilience, modulus of toughness? What is strain energy and strain energy density? Strain energy density, strain energy stored per unit volume. Okay, you see by this example. So strain energy density can be written as half stress times strain. So in the stress strain curve, the area under the curve gives you the strain energy density in the body. And if you restrict the area up to the elastic limit, it is this area, this value is called as the modulus of resilience. And if you consider the full area, it is called as modulus of toughness. So this is 2 marks question you may get. Okay. Now these are all not so important except the basic definition. Normal stress you should understand. This 2 marks only, it's nothing to do with the problem. Shear stress, you don't have to worry, you just have to know what it is. Problems you will not get. Multi-axial stresses, forget about it, don't touch it for the exam. So for axial load, so this is how we calculate. So P square L by 2AE. So again, the same slide number 9 is repeated again in slide number 15. Very, very important. Next is for bending. These two, slide number 15 and slide number 16, are extremely important. These two forms the basis of everything. So please note down. This you should know. What is the strain energy stored for an axial load? It is for P square L by 2AE. P square L by 2AE. For bending moment, it is M square by 2EI integral dx. M is the bending moment. Now throughout the beam, length of the beam, bending moment will keep varying. So strain energy stored due to bending moment is M square by 2EI integral from 0 to L. So integrated with respect to x from 0 to L. So these two are very, very important. I can't overemphasize. These two are very important. I'm reviewing only for these two. All others you can forget it. It is not required for us. Now, work energy principle, you can go through it as simple. Now, Castigliano's theorems. This Castigliano's theorems you will get for 2 marks for definition, or sometimes you get derivation. Okay. In this class, I'll not do the derivation, but the two theorems of Castigliano's I will state, and I will tell you when I'll be sharing with you the simple proof that has been given. Okay. If those of you want to score in this, you should study the proof also. Sometimes 2 or 3 times in the past they have asked proof of Castigliano's theorem. So in the linear elastic system, the partial derivative of the total strain energy stored in the body with respect to displacement at a point is equal to the force at the point. So total strain energy stored in the body is U. If we differentiate this partially with respect to a displacement at a point, we will get the force acting at that point. This is Castigliano's first theorem. Castigliano's second theorem states the other way. Interchange P and delta. What it says is the partial derivative of total strain energy stored in the body with respect to an applied force is equal to the displacement of the point of application application of that force in the direction of the force. So for a strain energy, body is written in terms of all forces. The strain energy is written in terms of forces, and you differentiate partially with respect to a particular force, we will get a displacement at that point. Now I'll be sharing with you, this is notes from a very good book, which of course you don't have purchased. It is not required for you. I am extracting and giving you. So it is Castigliano's first theorem and second theorem. Here they have not mentioned the derivative. I have mentioned the derivative there in the notes. So you have to state that, and then theorem 1 proof he has given easily here. Theorem 1 is proved here, and then uh, the validity of the second theorem. Theorem 2 is proved here. It is just 1 page. Okay. Those of you who wish to score on this, you go through this. All right. Next. So now I will first focus on this Castigliano's theorem. So in Castigliano's theorem, how is it that we find the deflection in the beam? So here, find the slope on deflection of the following cantilever at the free end. So understand the concept. This concept is used for all complicated problems also. Concept you should understand, you should be able to apply. So this is the beam of length L and the load W is acting on it at the free end. So we first calculate the bending moment. The bending moment at any section X is W into L minus X. All right. Once you do that, then we have to write the expression for strain energy U. The strain energy is integral 0 to L M of X M square by 2 EI dx. Remember, I usually prefer to take X only from the left hand side. Origin is at the left end, and X we calculate from the left side only. So some books give from the right side. You should not get confused. But if you are just following notes, this is sufficient. I am taking from the left side. So I get M as W into L minus X. So W into L minus X whole square by 2 EI. When I integrate and substitute the limits from 0 to L, I'll get W square L cube by 6 EI. Now U is this. By Castigliano's theorem 2, I want deflection at B under the load W. So wherever I need the deflection, there has to be a load. So load is already existing at B. So I want deflection at B. So partial derivative of U with respect to W gives me WL cube by 3EI, which is the standard result of the deflection of the cantilever beam. So this is how Castigliano's theorem is used. Now what to do to find slope? Slope at B. Now to find slope, there is slope is associated with moment. Moment will give rise to a change in slope theta. Load will give deflection, displacement delta. Moment will give theta. So to find slope theta at B, and I know that it will be clockwise rotation at B. So I will give a clockwise moment small m. So I am introducing a unknown moment. I call this as a fictitious couple moment. So I am introducing this. Fictitious means it doesn't exist. We are imagining it. So in addition to the existing load, I am giving this. So now I will calculate the bending moment. W into L minus X with a minus sign because it's hogging, and minus M again because it is hogging. So this moment plus this moment with the appropriate sign. So I get the bending moment at any section X throughout the cantilever. Now for the strain energy stored, again integral 0 to L m square by 2 EI dx. This m square I substitute m here now. Now to find moment theta, to find slope theta, I have to differentiate this strain energy with respect to this fictitious moment m. So that's what I do first. So theta b is dou m, dou u by dou m. So dou by dou m of u, this is this integral. Derivative of the integral is integral of the derivative. We can do that. So we can first take this derivative inside and differentiate. So when we differentiate, be very careful with the differentiation. We are differentiating what with respect to m, not with respect to x. So don't forget that. So this will be twice of w into L minus x plus m. Now this we can integrate. Now we have to integrate with respect to x. Differentiation with respect to m. This is second. So moment and theta are related, load and delta are related, displacement. Okay. So now when we integrate with respect to x, we'll get a solution like this. Then we have assumed m, right? But actually m is not existing in the original problem. So you have to substitute m is equal to 0. So here, once we get theta b, you substitute m equal to 0. When we substitute m equal to 0, we get whatever is the resulting value, that will be the slope, WL square by 2EI. Okay. So now the same Castigliano's theorem, we are using again to find the maximum deflection and slopes at for slopes at the endpoints and the maximum deflection of this simply supported beam with uniformly distributed load. Okay. So because we want the maximum displacement we know which occurs at the center, we have to take a fictitious load. Okay, now the question, I'll put a question. Now suppose it is given in terms of W here, but instead of W, if it was given 5 kilonewton load. So okay, you have to use 5 kilonewton load here, but P should be a variable. You cannot take P as 1 kilonewton or 3 kilonewton in Castigliano's theorem. Okay, P has to be a variable. I want to find deflection at C. So I will use load at P, fictitious load P at C. So I use that. Now, okay, now I need to find the bending moment for this combined case. So for the combined case, of course, I can split this as two cases and do a summation. So here the bending moment will have a single expression. Here the bending moment will have two expressions. You need to solve this and find the bending moments. So bending moment at this point is, RA. I have split this RA, RB. You go through this. See, this reaction times X minus the load minus X by 2. So WL by 2 into X minus WL square by 2. So I find the bending moment at this section, and for UDL throughout it is the single expression. But when it comes to load here, the expression for bending moment from A to C changes and from C to B it changes. So bending moment will have two expressions now by superposition. The first part will be common in both, but in the second part this will be P by 2x and this is P by 2 into L minus x. So this is from A to C. This is the expression for bending moment, and from C to B, this is the expression. Now, let us integrate. Only advantage is that this is a symmetric. Both are symmetric bending moments. It may always not be so. So, for symmetric bending moment, integral 0 to L m square by 2 EI, we can write as twice of integral 0 to L by 2. And we calculate in terms of, we write this expression, this is strain energy. Then using Castigliano's second theorem, the displacement at C will be partial derivative of the strain energy stored with respect to P. So taking EI common and differentiating and then integrating. After integrating, substituting the limits correctly and then substitute the fictitious force P equal to 0. Then we get the deformation. We get the maximum deformation at the center. Okay. Now for slopes, what should we do? Instead of using, I found the maximum deflection at the center. Now I want to find slope at A and slope at B. Now due to symmetry, slope at A and slope at B will be equal but opposite in signs. So if I find slope at A, I can find slope at B. So now I don't put the fictitious force P, that is not there, but I use the fictitious moment M in the direction of the slope theta. Here the slope of the endpoint in the elastic curve will be theta. It will bend this way. So moment will be in this direction. So in addition to W, I have moment and I write the expression for the bending moment. So I have to find R, which includes R reaction is not just for the load W, but it is also load W plus the applied moment M. So this is the reactions I get. Mx will be this expression. So strain energy will be m square by 2 EI dx. Then theta A, partial derivative of u with respect to m by Castigliano's theorem. Partial derivative with respect to the applied fictitious force. So then differentiate first and then integrate. So we simplify and then finally you put fictitious moment to be 0 and then simplify the terms. We get the same expression which we get in the first unit. Theta A is WL cube by 24 EI. Okay, so like that theta B also we can find, where theta B will be minus of theta A. That's all. Okay, before I enter into principle of virtual work, I will go further uh, in Castigliano's theorems only, because virtual work principle I have to explain more detail. Okay, this is the one. So now I am taking another example for beam by Castigliano's theorem. So here in this notes I have mentioned that definition and proof of page 33, 34, 35 by this book. So which I have already included here. I will be sharing with you. Now, application to deflections, Castigliano's theorem, we are continuing from there. Okay, this was the notes which I originally had given you. Okay, which I have done in the class. These are the additional problems which I am telling you today. So now find by Castigliano's theorem the deflection at the midspan of AB. AB is a simply supported beam loaded at C, 1/3 of the distance. Okay, but I want to find the deflection at midspan D. So what I do, I introduce a fictitious load. So here we can write P or we can write WD. Okay, I'm giving different notations. You can write P here, doesn't matter, or WD, load at D. This is a, let us apply the fictitious load WD at D acting vertically downwards. Now analyzing the beam. So now we find the support reactions. Okay, support reactions due to 120 load, it will be W B by L. Okay, AB. If you remember the formula, if load W is acting at a distance of A from the left hand and B from the right hand, and A plus B is L, then reaction here is W B by L. So 120 into this longer span 4 by L is 6. Okay. Plus now WD will act centrally, right? So it will distribute equally WD by 2, WD by 2 at A and B. So at A, from 120 kilonewton load, we'll get 120 into 4 by 6. That much portion A will bear plus WD by 2. So you get 80 plus 0.5 WD. Next, RB will be 120 into this side 2 upon 6. 120 into 2 upon 6 plus WD by 2. So RB, RA and RB I found directly by formula. Otherwise you have to do sum of the vertical forces is 0 and then take moment about A and calculate RB and RA like that. But by now with this practice you should be able to find RA RB very fast. Otherwise you will not be able to solve big problems. Next, now bending moment in various sections of the beams. Now you see I have to do integral m square by 2 EI dx over the entire length. But my m bending moment in segment AC will be different, in segment CD will be different, in the segment DB will be different. Whenever there are point loads, the bending moments change. So for segment AC, the bending moment is RA times X. So it is simply 80 plus 0.5 WD times X. So this segment X varies from 0 to 2. Next segment CD. In segment CD, you have RA times X minus 120 into X minus 2. This X is at this distance. All right. So at any point here, the bending moment will be RA into X minus 120 into x minus 2. So this is the bending moment. We simplify this and write like this. So this is the bending moment expression between 2 and 3. And at WD, between D and B, the bending moment you can calculate from the right, RB times 6 minus x. So we have done RB times 6 minus x. We can simplify it further or leave it here. Now we find the strain energy. The strain energy here is, you see here, m square by 2 EI. Now throughout EI is constant. Okay. E and I are constant throughout. They are not changing. So E and I you can take out. All right. Or leave it at the bottom. You have this. So this is the expression for the bending moment from expression for strain energy, m square by 2 EI dx. Now 0 to L is split into 0 to 2, 2 to 3 and 3 to 6. So 0 to 2, 2 to 3, 3 to 6. X varies from. So this is the first segment, AC, then CD, and then DB. This one, 3 segments. Now we differentiate with respect to WD, the fictitious load. So when we differentiate this, okay, we have to very carefully differentiate. You are differentiating with respect to WD. So you will get expressions. You have to be very careful of how you are differentiating. And then once you differentiate, after that you do the carry out the integration. And once you do the integration, substitute WD is equal to 0. Substitute WD is equal to 0. All right. So when you substitute WD equal to 0 and simplify, you will get this result. So this is your delta D. Now you finally substitute EI. Remember, don't make the mistakes of units. Now this is in kg kilonewton meter cube after integration. How is that so? Because moment is kilonewton meter. Moment square will be kilonewton square meter square divided by load. Na? Load is coming in the denominator. So kilonewton. So the numerator will be kilonewton meter square and we are integrating with respect to x. So kilonewton meter cube. This you should remember. This will be kilonewton meter cube. Once you do kilonewton meter cube, now divide by EI. So kilonewton converts to 10 to the power 3 Newton. And meter cube will be 10 power 3 mm whole cube. That will be 10 power 9 mm cube. And then write the Young's modulus is 200 GPa, that is 200 into 10 to the power 3 MPa, and 1 MPa is Newton per mm square times I. So you get this value. Okay. So Castigliano's theorems. So you practice more problems on this. These are for beams. Okay, 3 problems we have done for beams. All right. The 3 you practice nicely and you take. I am sharing you this book. In addition to R.K. Bansal doesn't have so much treatise on energy theorems. He is not given. But this strength of material books are Subramanian, very, very good book in for these topics. So, and it has some good examples of fixed and continuous beams also. You can go through that. Now, Yeah, strain energy, Castigliano's theorems. So he has given some problems. You can attempt to solve those problems. One or two examples. Common ones you don't do. Some load problem, like a problem like this. 10.27 Castigliano's uh, theorem under strain energy. This is load. Find the deflection at the free end. This is a typical question, and you can practice this and solve it. Okay, Castigliano's theorem for frames you ignore. Okay, then all right. Next, so one or two more examples from this book you can do. This is for beams. Now let us move forward. I want to do Castigliano's theorem for frames, for trusses, which are called as pin jointed frames. Okay, so I hope you all have a basic concept of trusses. I will show trusses. I have redundant. What is a truss member? This is a truss. We'll come to determinacy and other things. So these are trusses. Trusses are, every segment will form a triangle. That is for a stable truss. So these are trusses. Pin jointed because the ends, we assume that they are jointed by pins. They are smooth to rotate. So therefore, in trusses, any member you take, they are not subjected to bending moment. They are subjected only purely to axial forces. So trusses are axial force members assemblage. It is the assembly of axial force members. Now strain energy stored in a truss member subjected to a force P. If the member force is P, right? And I told you in the very first, I asked you to remember this, that for bending moment and for axial load, the strain energy stored for a bar subjected to axial load P is P square L by 2 AE. So the same thing we will do now here. So the strain energy stored in a truss member subjected to a force is given by half Pi delta, and delta is P L by AE. So we get P square L by 2 AE. Now I'm writing this I because it is the ith member. It is the ith member of the truss. Okay. Now total strain energy stored in the entire truss is sum of all the strain energy stored within each member. So let's say the truss has n members, so it will be P square Pi square Li by 2 AIE. Now usually AE is constant. Area for each member, we take uniform bars. So A is constant usually and E is also constant, the Young's modulus for across each member. So now by Castigliano's theorem, I want to find a deformation at a particular point or a particular member force, a deflection in a particular member or deflection at a joint. Then what I do? Deflection at a point of application of a force Q. So wherever I want deflection, I can put a force Q, a dummy fictitious force, and find out all the member forces. So all member forces will be in terms of Q, and then differentiate partially So U will be in terms of Q. I differentiate U partially with respect to Q. So I get 2pi, derivative of P square is 2P into dou P by dou Q. So then 2 cancels. So upon differentiation, I get Pi, dou Pi by dou Q, and L by AE remains as it is. So this expression you have to remember. This is a very, very important expression. Just a second. This is a very important expression. I don't know why pencil is not writing. It's writing. So, okay. Anyway, this is a very important expression. I want you all to take a note. How do you get P square L by 2AE? You differentiate with respect to a force. Now, P will be a function in terms of Q. So this will be 2P dou P by dou Q. So this is the crux of finding formula for deflections in truss. So let us do one problem. So let us look at this problem. Now the cross section area of each member of the truss is shown here. Pay very careful attention to this problem. I'll go a little slow in this problem. Later problems I'll go a little fast. Now determine the vertical displacement of joint C. Vertical displacement of joint C if 4 kilonewton load is applied to the truss at C. Now this is truss ABC. This Q is not there. Given figure is only this 4 kilonewton load. I want, see, when I apply this 4 kilonewton load, as the C displaces to the right, it also displaces towards down slightly. All right, because slightly when C displaces towards right, it also goes downwards. So I want to find the downward displacement. Determine the vertical displacement of joints. So for that, I will take a fictitious force Q along the downward direction. Okay. So let fictitious force Q be applied at C vertically downwards. So now I have applied Q and I have taken the free body diagram. I have, RAX, RAY, RB or RBY here. And very, very important, assume that to start with, to do truss analysis, assume that all the member forces are in tension. Okay, this I'll have to explain. Just a second. Just hold on. So you have done trusses in engineering mechanics course. I'm just reviewing that. Okay. So what we just discussed here is this. Okay. So, see, generally, yeah, in a truss, let's say this is a truss element. These are two joints of the truss, A and B. They're joints. Now, I'll, oh, this joint AB. Now, if the member AB is in tension, okay, this is member AB, this is in tension. Tension means its length is being elongated, right? So member is in tension. But on the joint, what will be the effect? The joint, because it is in tension, it is like the joints are pulling the members on either side, and the member is pulling the joint. The member is pulling the joint. So this is joint A, and this is, say, joint B. Here I'm just extracting like this. So member is being pulled apart. It's in tension. So the member is also pulling the joint in return. Okay. So see, when you try to take a string and pull it between your two hands, then it appears that the string is also pulling you. So always in trusses, we write arrows like this. These are not forces on the members. These are the forces on the joints due to the member force. It will be the same. Let's say this is FAB. This will also be FAB. This will also be FAB. Okay. So writing like this, member forces like this means we are assuming that the members are in tension, FBC. All right. These are like forces acting on the joints because we will use the method of joints. So that is what I have shown here. I've just put the joints here and the member forces I've written FAC. FAC will act both at A and at C. So FAC is the force in the member AC, force in the member AB. So always point away from the joint. That means the member is in tension. FBC again. So always mark the forces away from the joint. So it is in tension. When you solve, if you get negative, it means that the member is actually in compression. So you don't have to worry on that. So once I've marked like this, I have marked theta. So theta here, this is 4. This length is total 8. So midpoint is 4 and height is 3. So 3 square plus 4 square under root will give you 5. So this is 5. So sine theta is opposite side by hypotenuse 3 by 5. Cos theta will be adjacent side by hypotenuse 4 by 5. Okay. Now, after that, what we need to do is using equilibrium solve for the entire thing. First of all, we have to do is consider the truss as a one single body and find the support reactions AB. Just like if you consider this as a rigid body, then the external forces must be in equilibrium. Forget about the internal member forces. consider this A, B, C as a solid body, then the external forces must be in equilibrium. So Rax, Ray, Rb, 4 kilonewton and Q should be in equilibrium. So we do sum of vertical forces equal to 0. That gives us Ray plus Rby is equal to Q. Then sum of horizontal forces should be equal to 0. So Rax plus 4 is equal to 0. So Rax is minus 4. Minus 4 means this was our assumed direction, but actually Ra will be in opposite direction. That is the meaning of minus. Next, I want to find Rb or Ra, right? So what I'll do, so if I take moment about B, so Ray times this distance 8, so Ray times 8 plus due to Rax, the moment will be 0 because Rax passes through the point B. The line of action passes through the point B. So there will be no momentum. Whereas for Q, let me try to copy this. Okay, just a second. So we have to use the concept to find moment, that moment at B due to Q is Q times the perpendicular distance of the line of action of Q from this point B. Okay, so it will be Q times this length, that is 4. Okay, so let's go back and see. So it is Q times 4. Now Ra into 8 clockwise is positive, so Q times 4 will be negative. Then due to this force, 4 kilonewton force, again what you have to consider is the line of action of force and the distance of the point about which we are finding the moment. This is 3. So 4 into 3. Okay, force times the perpendicular distance. So Ray into 8 plus 4 times 3 minus Q into 4 equal to 0. So from here we get Ray is Q minus 3 upon 2. Ray plus Rby is Q. So Rby will be Q plus 3 by 2 upon simplification. Now we found Ra and Rb. Now we have to find uh, the internal member forces. Okay, for this one. So what will be the internal member forces? Go to joint B. Now take each joint at a time and apply the equilibrium condition. Sum of horizontal forces equal to 0, sum of vertical forces equal to 0. So first one, I have done sum of vertical forces equal to 0. And of course, I hope you know how to do the components of force by now. It's very, very important. So if this is theta and this is our force F, all right, the component of force in this direction adjacent to theta will be F cos theta. And the component of force in the perpendicular direction, this is theta. So this may be 90 minus theta. So in that direction, 90 minus theta direction, this will be sine theta, F sine theta, F sine theta, F cos theta. Okay, basic engineering mechanics. So Now this is theta. Along this FAB, the component of FBC will be FBC cos theta, but I want vertical, so FBC sine theta. So FBC sine theta plus RB will be equal to 0 because at B, sum of the horizontal force, sum of the vertical forces equal to 0. So I do this FBC into sine theta equal to RB. So FBC sine theta is 3 upon 5 I mentioned earlier plus Q plus 3 by 2 equal to 0. That is RBY. So FBC you get simplifying as minus 5 by 6 Q plus 3. Now similarly FBC cos theta plus FAB is equal to 0. So FAB plus FBC cos theta equal to 0. So FAB will be FBC into cos theta is 4 by 5. So FBC is this, substitute and find FAB. So I've solved for two member forces. Then go to joint A or joint C, whichever doesn't matter. So go to joint A. Now sum of the horizontal force is 0. So RAX plus FAC cos theta plus FAB. Don't try to change based on the sign and all. We know that RA is minus 4. So don't change the direction of RA. Keep as it is. Just substitute whether it is plus or minus. That's all. So RAX plus FAB plus FAC cos theta equal to 0. So RAX is minus 4. FAC into cos theta is FAC into 4 by 5 plus FAB. All right, FAB we found from previous thing. Now you simplify, you will get FAC. So we found FAC, FAB, FBC, FAC. So all three we have found, all three member forces we have found. So now after that we should write a table like this. Why? Because we have to do summation. Remember, we have to do this summation. Summation involve member forces, partial derivative and length. So and AE. So let us do this. Of course, AE is common. So you can omit AE and at the end you can put AE, doesn't matter. But this is the method. Member, you write the member AB, BC, AC. Length of the members, AB is 8, BC and AC are 5. You have to calculate the lengths. Okay. 5, 5, 8. You have to calculate the lengths if they are not directly given. Then member force P. So FAB I found out. FAB is 2 by 3 Q plus 3. Then FAC and FBC minus 5 by 6 Q minus 5 by 6 Q plus 3 minus 5 by 6 Q minus 3. Now for this expression, differentiate this partially with respect to Q. You have found P, member force, differentiate this partially with respect to Q. So differentiating with respect to Q, you get 2 by 3. Here you get minus 5 by 6, here minus 5 by 6. Now what you have to do? P times dou P by dou Q times L. So column 2 into column 3 into column 4. These three you have to multiply. So when you multiply, you get 32 by 9 into Q plus 3. Then remember, fictitious force we have to substitute to 0. Once we found differentiate and add the strain energy. So at this juncture, after differentiating and multiplying, I'll put Q as 0. So I multiply here and put Q as 0. So I get 32 by 3 AE. Same for member BC. L into P into dou P by dou Q. Put Q equal to 0. And you get this. And finally you get this. Same. Okay, the common procedure. This into this into this, you will get this. After that, you add. So by doing so, you are getting this expression in Castigliano's theorem. That is equal to delta directly. Once you substitute Q equal to 0, after that, dou P by dou Q, dou U by dou Q you have done, and then put Q equal to 0, you will get deflection. So delta Q straight away you will get as the deflection, vertical deflection at Q. And you substitute this value, 10.67. This is kilonewton meter. Again, be thoughtful. Uh, how you do. In bending moment case, it was different. In bending moment, it is m square by 2 2EI. Here it is AE. So you have to be careful. How you will get? It is P into dP by dQ into L. So P is kilonewton, Q is kilonewton. Again, dP is in kilonewton. So only single kilonewton times length, kilonewton meter. This is not kilonewton meter cube. That is only for bending. For axial load, the unit in the numerator will be kilonewton meter divided by area into Young's modulus. You have to cross check your units. Units should be mm here. So we convert 10.67 into 10 to the power 3 Newton into 10 cube mm divided by area 400 mm square and Young's modulus 200 into 10 cube Newton per mm square cancels, Newton cancels. The final resulting units is mm. So our this expression is correct, kilonewton meter in the numerator. So upon substituting, we get 0.133. This is how we solve for the truss member. Okay, this is example of a Castigliano's theorem for trusses. Okay, I had for more examples, two things. You can either go to the textbook, the Subramaniam textbook, or I had shared with you Ashwin sir's notes, Ashwin sir of Mathurashri Engineering College. All right. He has done problems only based on Castigliano's theorems. He has not done unit load method. He has done Castigliano's theorems. They are good ones for practice. You can take this and try to do. Some are simple ones. You see here using Castigliano's theorem. Vertical deflection, horizontal deflection, one problem. And then this is a truss. There's this problem. So you can study his notes, unit 4. And towards the end, he has given redundant trusses based on again Castigliano's theorem only. Okay. So 3 or 4 problems, if you go through what he has done, remember these problems by reading you will not get. First problem may take half an hour, 45 minutes for you to solve one problem. No, don't worry about it. Do another problem. It will take, say, little 5-10 minutes lesser. Do another problem. It will take more lesser time. So less than half an hour you will be able to. But three problems at least if you practice, then you will get. So Ashwin sir's notes are full of Castigliano's theorems questions only. And towards the end, he goes after, this is page number 10. He goes to redundant frames. So redundant frames method I will explain later. But, first 8 pages of Ashwin sir's notes, you go Castigliano's theorems problems. So this is about Castigliano's theorem of how we use for trusses and how we use for beams. Maybe I should, yeah, Ashwin sir's notes here. Yeah, it's a slightly bigger truss. There's a bigger truss. This kind of problems you can expect. So 4 meter, 4 meter, 4 meter. So 45-degree angle. So it's easy to do. And 45 kilonewton force is applied here. Determine the vertical deflection at the free end of the truss shown. Cross-sectional areas are in square centimeter. The areas given here. Okay, in this problem the areas are changed. 30, 30, 60, 60, 30. And then square centimeter. You have to convert to mm. Alright. So this was a previous question paper, June 2007. And now he has solved it. So something very interesting. Now, if you have something like this, you don't have to find the support reactions first. You go to this end joint. At any given joint, there should be two unknowns and other should be known. So at E, the unknowns are these member forces. So at E, you will get FCE and DE. So FCE sine 45 upwards. So this is PCE sine 45 minus 45 minus Q downwards. When you add up this, you will find PC in terms of Q. So you will get this expression. Then when you do sigma Fx equal to 0, this PCE, he has written force as P. So, so PCE plus PDE, PCE cos 45 plus PDE is 0. So PDE will be PCE okay PDE okay PCE cos 45 and PCE sin 45 are the same thing. So this you write as 45 minus Q from here. So PDE will be 45 minus Q. Mine, you just have to check the signs properly, that's all. Correct, minus 45 minus Q. And then first, after you find from joint C, go joint E, go to joint C, because again, this is known for you. This is known. You should not go to joint D. If you go to joint D, this is unknown, this is unknown, this is unknown. Three unknowns and two equations only you will have. You will not be able to solve. So from E, you have to go to C. At C, this is unknown, this is unknown, this is known. So this is known, this is unknown, this is unknown. So again, sigma Fx equal to 0. You will get force in BC and force in CD by sigma Fy equal to 0. You will get that. And then similarly, joint D. Joint D also you can do. Then you found this and this. So all member forces you have found. Now, when all member forces you have found, then member length, now area also comes because area is changing. Then load, then its derivative with respect to Q, and then do this P times dou P by dou Q into L by AE. So P L by AE into dou P by dou Q. You do it and put Q equal to 0 in P. So so this final calculation he has done. I don't know whether he has done E. So delta E finally he has found to be 2.9 mm. So here he has done the calculation. He has not shown E, but through calculator he has done the calculation and do it. Done. Otherwise you can put E at the end and divide at the end instead of dividing E each time. Whichever is the common factor, you can add and finally divide at one go rather than doing each time. Okay, so this is Castigliano's theorem. All right, just breathe for 2 minutes, 2 minutes break. So Castigliano's theorems questions come, that's why I'm emphasizing it more. Now we will do theorem of virtual work. Just 2 minutes break, just absorb. How many of you are present? Okay, only 12 of you survived. Okay. Next is the principle of virtual work. We'll start that. This is a concept little uh, more involved than Castigliano's theorem, in fact, but it's a very powerful method of finding a solution. So these are the books from which notes are given. Principle of virtual work, you don't have to find the proof, but the concept, you understand the concept. What is the concept? So what I want is, see, this Castigliano's theorem and the virtual work principle or unit load method. The advantage is that anywhere I want to find the deflection, there I'll apply a force and find a deflection. I don't have to find the entire elastic curve. Like in unit 1, we did double integration of m by ei and did a double integration and found the elastic curve y. So it is not necessary. I want to find at a particular point. So for example, here, this is a beam. It is loaded at 3 points of the beam, 1, 2, and 3, W1, W2, W3. But I want to find the deflection at another point C. Now I don't have to find the full elastic curve and then substitute the value C to find this. I'll do a unit load method. Now, for the unit load method, the concept is like this. The proof, this proof, I don't want, the proof is explanatory. What we are doing is, work done by the loads is equal to the internal strain energy. So the work done by loads W1, W2, W3 all applied simultaneously but gradually will be half W1 delta 1, half W2 delta 2, half W3 delta 3. This is the work. Is internal strain energy stored. Now this is the beam AB segment. There is a fiber. The fiber will experience compression. So when there is compression in the fiber, okay, this is a compressive stress. So compressive force F is acting. Force times the deformation, the compression, internal deformation dl due to the applied load is this. So half sigma FDL. This is the first equation. Now what in this is the basic energy equation for the given problem. I want to find delta at C. For that, what I do, I assume that first a unit load is applied at C. No, so assume a unit load 1 kilonewton applied at C to produce a deflection delta C. So due to the external loads, the deltas are capital delta 1, capital delta 2, capital delta 3, capital delta 3, delta. Here it's a small letter delta in Greek alphabets. Delta 1, delta 2, delta 3 and delta C. Okay. Now this is due to unit load. Now due to unit load, the internal strain energy stored is 1 half into 1 kilonewton into delta is equal to half times load times displacement. The internal strain, the compressive strain in the member. So now, so first we assume to solve this problem that first a unit load is applied at C. After that, the loads W1, W2, W3 are applied, keeping the single 1 kilonewton load as it is. So first there was deformation delta 1, delta C, delta 2, delta 3. Now the deformation with W1, W2, W3 added on will be delta 1 plus delta, delta C plus delta, delta 2 plus delta, delta 3 plus delta. So first unit load is applied and then after that the actual loads, external loads are applied. And then we get a equation of work done and internal strain energy. Okay. So here unit load is already present. So the additional delta, the work done will be 1 times delta. So after that, you combine in the two steps the work equation and finally eliminating the common terms, you get this expression. So even if you don't understand the proof, this you have to understand, very, very important. Unit load multiplied by the deformation at that point due to the external applied load is equal to sigma of internal forces times dl. So work done here, uh, you know, is strain energy stored within the body. Strain energy is force times again displacement, internal force times internal displacement. So here you see 1 and this u are virtual loads. It is actually not existing. We are applying that one load, and due to this unit load, the internal forces that are produced are these. And the product on the right products are the real displacement. Virtual loads, real displacement. 1 and sigma u, delta and dl. This concept has to be very, very clear. Okay, you go through this. So virtual unit load in the direction of delta. U is the internal virtual load acting on the internal fibers in the direction of the internal deformation due to unit load. Okay. Delta is the external displacement caused by real loads and DL is the internal deformation caused by due to real loads. Same expression we can also do for theta, not just for delta, for slopes also. Instead of unit force, we apply a virtual unit moment, unit couple. 1 times theta is sigma u theta dl. So virtual loading, real displacements. So this is the concept. Now, very important, this is applied in two ways for trusses and for beams. First for beam. For beam, the internal stress and internal force in the fiber due to the virtual bending moment due to unit load, small m, here is the bending moment developed at the section under consideration due to unit load. So m by I is equal to F by Y. So F is m by I into Y. Now force will be F into area times dA. So this is U. And dl is the displacement due to the actually applied loads. deformation, internal deformation in the fiber due to applied load. That will be My by EI dx. Again, the same concept of bending stresses. Okay, M by EI. Uh, this is uh, this is strain basically. So stress is M by Y times I. Stress by Young's modulus is strain. Strain times the length. Length of the original fiber is dx. So we get this. So finally, even if you don't remember all this, when we multiply UDL and do a sigma, then we have to do, if it's a continuous, we have to do an integration. And upon integration, this integral 0 to a y square dA becomes I, the Young's modulus of the cross section, so it cancels. So delta, this result is extremely important. 1 into delta, unit load, unit virtual load into delta is integral of 0 to L. Capital M is the moment, bending moment developed due to real loads, multiplied by small m. It is bending moment due to the applied virtual load divided by EI dx. Okay. So for slopes, this is. So finally, you just have to remember this. You don't have to remember all the methods. Application to beams. 1 into delta is 0 to L capital M small m by EI dx. So now application to, so in my original problems in class, I have done this. I didn't explain that time the entire detail, but by virtual work principle, I told very simply 1 into delta is integral 0 to L small m capital M by EI dx. Small m is bending moment at a section x due to unit load. Capital M is bending moment at a section x due to real loads. So here, so I have a cantilever with a uniformly distributed load. I want to find the deflection at the free end. So I introduce a unit load at the free end. Okay. Now I will split this into two parts. One is bending moment due to unit load at B. So bending moment due to unit load at B is 1 times L minus X. So minus of L minus X. Now bending moment due to real load, this uniformly distributed load. So you get W into L minus X into L minus X by 2. So minus W L minus X whole square by 2. Now by the principle of virtual work, 1 into delta B is integral 0 to L small m capital M by EI. Small m, you substitute the expression for moment, expression for capital M by EI, and you integrate, you get the same result WL square by 8 EI, which we get by double integration. WL power 4 by 8 EI. Okay, I have done this in class. Then if I want to find theta, instead of using the virtual load of one unit load of 1 kilonewton virtual, I use couple moment of 1 kilonewton meter. And again, I find the bending moment. It's constant here, -1. Here it is WL square, W into L minus X whole square by 2. So M by EI. Okay, this is not strain energy, this is virtual work. So remember integral 0 to L M by EI, small m capital M by E. That's what you get. Okay, so this is the principle of virtual work applied for and once you solve this, you get theta B. So this is the principle of virtual work applied for both uh, beams. Now let us do for trusses. I have done a number of problems. You go through it. And in this notes also, yeah, go through these notes, very, very important for unit load method, virtual. So here I want to find the same problem which I did for using Castigliano's theorem. I'm doing by unit load. In Castigliano's theorem, we use a fictitious force P or WD here in this case, but here we'll use a unit load. So first, due to real loads, I calculate the bending moment in segment AC and segment CB. Then due to the unit load at D, I calculate the bending moment in segment CD and segment CB. Then this is small m, this is capital M. Then I draw a table like this, segments AC, CD, DB, capital M, small m. Now, so we have to divide into three segments, A to C, C to D, D to B. So A to C, C to D, you know, this small mx will be common. C to D, D to B, this capital M will be common. Anyway, so once you do this, then small m, capital M by EI, limit integration. So EI is constant, so we do that and we integrate and we calculate the integral carefully. Exactly the same value of deformation you get. Remember one thing again, here 1 is kilonewton in the left hand side. On the right hand side, it is kilonewton square meter square. So this 1 kilonewton divides one of the kilonewtons here. So you will get kilonewton meter square integration. After integration, you will get kilonewton meter cube. So remember this and find delta. So now this is unit load applicable to beams. Now I'll just take 5-10 minutes to explain the unit load method applicable to trusses. Okay. So for unit load method to applicable to truss, again, virtual load times delta is sigma u dl. Now this u works out to be the forces in the members due to the unit load, small f. Okay, F or UI is axial force in the ith member due to unit load. And delta L is the change in the length of the member due to applied loads. Okay, due to the applied load. This change in length is due to force, applied member force. You know, F is axial force in the member due to external real loads. So FL by EA. So FL by AE or EA is the real displacement of the members. This is the virtual forces. Virtual force times real displacement is sum of the virtual forces times the real displacements. So remember that. So forces are virtual, displacements are real. So displacements are real means the displacements under the real forces. Capital Fi is force in the member due to external real loads, whereas small fi is force in the members due to virtual loads. So this is how we do. Now the same problem what we have done earlier, we got 0.133, exactly the same problem using virtual load method, unit load method. What we do, I have this problem. I use this 4 kilonewton load and find out calculation of member forces due to applied load of 4 kilonewton. So using method of joints, I find out all the member forces FAC, FAB, FBC, 2.5 to minus 2.5. I find this. Then now after this step is over, now I come to calculation of member force due to virtual load 1 kilonewton. So I want to find a deformation of member C vertically downwards. So I am taking virtual load in that direction only, 1 kilonewton. Now this 1 kilonewton, I apply the load and I found the member forces. I'll write it as small f. So I calculate small f. So small f AC is minus 5 by 6, small f AB is 2 by 3, and one more. Yeah. FAB, FAC, and FBC will also be the same. FBC, FBC, FAC by symmetry, FAC is equal to FBC. So now I write member, I write small f, which is forces in the members due to unit load. Now capital F, forces in the members due to applied load, the actual real loads. This is the length. And of course, if area and Young's modulus vary, then A by E has to change. So, but here AE is constant. So I am just considering F, small f, capital L. I multiply. When I multiply that, I get this result by AE if I do. So I'll get kilonewton meter by AE. I get exactly the same value, 0.133. So this is the method of virtual load unit virtual work, that is unit load method applied for trusses. Okay, this is another example. You can do this by Castigliano's theorem also, and this is by unit load method. Okay, first find the member forces due to external real loads. All FABs, all F's, capital F's we have found. Next, due to virtual unit load at E, because at E I have to find the deflection. So I apply. And then he is asked for total deflection of E. So I apply at the horizontally applied load also. I find this. Then I make table force in the members due to real loads, force due to vertical unit load applied, due to horizontal unit load applied, member, and then the two cases force capital F, small f, vertical, L, capital F, small f, horizontal into L, and we do the calculation. And we get the vertical deflection, we get the horizontal deflection, and we get the net deflection. Okay, and you go through this. So today I stopped with this. I could not complete the redundant forces, redundant trusses, but I will share the notes with you right now. Go through these. It will take 3-4 hours for Castigliano's theorems and virtual work. At least 4 hours it will take, but if you want to get a full grip, you should put full effort into this. You will get a full grip onto this. I'll be sharing these notes right in the MS Teams right now. Okay. Thank you. Thank you. I'm stopping the recording.